So in this video, we're going to continue solving for our v of t, since from our previous video, we're tasked to solve for a differential equation for our velocity v of t. So we found a first order nonlinear differential equation which is the dv over dt is equal to g minus kv squared over m, right? So we successfully found this one. This one is a formula for our acceleration, since the acceleration is just the instantaneous change of velocity over the instantaneous change of time. So we got a formula for our acceleration. Now we're going to find the velocity v of t. So we're now trying to find the velocity v of t, and we're going to express our answer in terms of our terminal velocity. So we talked about terminal velocity last time too, and the equation vt is equal to m squared of mg over k. We're going to go talk a little bit of our terminal velocity here. So our terminal velocity actually is or has this formula. So I'm going to explain a little bit of these formulas. So basically, m is the mass of the skydiver that's fallen downward, right? So it's the mass of the free fallen body. So this means the terminal velocity here, since it's directly proportional to the square root of the mass of the skydiver, this means that if your object is heavier, that means you're gonna go get a higher terminal velocity. So the higher your m, the higher your terminal velocity. So it takes for a heavier person to have a higher terminal velocity. It will reach that certain velocity where its acceleration will become zero, but it has to be bigger compared to the skydiver who like actually weighs lesser, right? So if your mass is greater, your terminal velocity will gonna get higher compared to the mass, which is actually lesser. How about k? The value of k is dependent to the drag coefficient c. This is the drag coefficient c, drag coefficient, and it's also dependent on the area of the object that's fallen, the cross-sectional area of the object that's fallen. And it's also dependent on the air density. So these are the parameters that affect the value of your k. The drag coefficient, the cross-sectional area of the object that's on free fall, and the air density of the fluid or the air. So that means, so we're going to focus on increasing the k by increasing the a. So if we increase the k, what happens to your terminal velocity? It's going to go down, right? Because your terminal velocity is inversely proportional to the square root of your k. So if you actually increase the value of your cross-sectional area, you decrease the terminal velocity. So this means that if a skydiver spreads its body, it's increasing as it falls, it's increasing its area, right? To increase the cross-sectional area of the object, you have to spread out your body, right? So it's spread out posture. That means it increasing your cross-sectional area increases your k. So if you increase your k, you actually decrease your terminal velocity. So if you want to go get a higher terminal velocity, you just head first dive. So that means you do like this. So that means you're reducing the cross-sectional area, right? If you're the object that's falling and then you're changing your position like head first, that means you're reducing the cross-sectional area. If you're reducing the cross-sectional area, you're also reducing the k, because k is directly proportional to the cross-sectional area of the object that is in free fall. So that means if you reduce the k, that means your terminal velocity also increases. To decrease your terminal velocity, you just go spread out your body, and if you want to increase your terminal velocity, you just go head first. Let's go solve for v of t, and we're going to use vt, or the terminal velocity. We're going to use this, and we're going to express our v of t in terms of vt, mj, and k. Okay, so let's go solve for this one. It would have been easier if our differential equation is an first order linear differential equation. It just so happens that our differential equation is just the first order nonlinear differential equation. It's nonlinear because we have v squared here. If it was just v, it could have been linear. So it's not linear. It's a first order differential equation, but it's non-linear. So we're gonna go solve for v of t. So the first thing we're gonna do is to separate the variables. So all of the terms contained in v will go move it to the left hand side of the equation, and all of the terms contained in c will move it to the right hand side of the equation. So easy peasy, we're gonna go multiply both sides of the equation by dt over g minus k over m v squared. So this one here times this one, you just cancel dt, so you'll get dv over g minus k over m v squared is equal to, multiply this one here to this one, so you just cancel this, you'll get tt. So now that we've separated the variables, we're gonna go integrate both sides of the equation. So how do we integrate both sides of the equation? We go factor these out first. So we're gonna go g minus k over mv squared. We factor these. So as you can notice, this could be expressed as the difference of two squares, right? So we just make this square root of g squared minus square root of k over m squared v squared. So these is just the difference of two squares. So factor these out. You just go, you remember difference of two squared, a squared minus b squared is just equal to a minus b times a plus b. So that's how our a is square root of g, so we write square root of g minus our b is square root of k over m times v. So we write that as this one, and our a square root of g, our b square root of k over m v. But this is a plus sign because this is difference of two squares. Now that we've factored out this one here is j minus k over m v squared. So now that we're done factoring these difference of two squares, we're gonna go look for a partial fraction decomposition of the expression 1 over g minus k over m v squared. We can go set let a here over one factor of this one is square root of g minus square root of k over m v plus b over g plus the other factor of this difference of two squares is this one. So we use that square root of g plus square root of k over m v. So now we go multiply both sides of the equation by the factors itself of this one. Square root of g minus square root of k over m v times square root of g minus square root of k over m v. Oh no, I mean this is plus sign. Don't forget that one. So let's go multiply this one to this here. So this will be left with 1 here is equal to a times what's cancelled if we multiply this expression here to here. The one that will be cancelled would be this one, right? So we would be left with a times square root of g plus square root of k over m v plus b. If we multiply this to here, so what's cancelled? These, right? So we'd be left with this one. So b times square root of g minus square root of k over m v. So now we'll go look for the value of a and b. So if we set v is equal to square root of m over k, but we'll go multiply it with g. So that means our equation would be 1 is equal to a times square root of g plus square root of k over m times v, which is this one, square root of mj over k plus b times square root of g minus square root of k over m. Our v is square root of mg over k. So now we can cancel these things here. Mk, so we'd be left with square root of g, right? So that's 1 is equal to a times square root of g plus this one here we can also cancel. So we'd be left with square root of g plus square root of g plus b squared of times square root of g minus square root of g. So this term here would be 0, so we'd be left with the variable a. So we can actually get that value 1 over square root of g plus square root of g is just square root of, or 2 square root of g. So same thing, we're looking for the value for our b. We set v is equal to negative square root of mj over k. So we now have 1 is equal to a times square root of g plus square root of k over m times v is negative square root of mj over k plus b times square root of g minus square root of k over m times our v is negative square root of mj over k. So that means 1 is equal to a. So we can actually cancel these things out. K square root of k over m, square root of m over k. So we'd be left with square root of g minus square root of g plus b square root of g minus, we can cancel these things out here, k and m. So we'd be left with square root of g minus negative square root of g. But square root of g minus negative square root of g is just the same thing as saying square root of g plus square root of g. So we'd be like, we will delete this and we'll change it to plus. So this is 0 here. So this is 1 is equal to b times 2 squared of g. So that means our b is also the same thing as our a. That's 1 over 2 squared of g. So our b and a, we have values. Now we can actually plug these in our partial fraction decomposition, which we set earlier. So that's this one here, we plug in our value a and b here. So we'd be getting 1 over j minus k over mv squared is equal to, that's a over square root of g minus square root of k over mv, right? Plus b over square root of g plus square root of k over mv. So we just changed the value of b, which is 1 over 2 square root of g, and the value of a is also 1 over 2 square root of g. So this is the partial fraction decomposition, and we're gonna go have it in our integral. We'll go incorporate it and take the integral of these, because we now found the partial fraction decomposition. We'll just plug it in here, what we found inside our integral, and we're gonna go solve for our integral. That's square root of dv over this. So let's just go rewrite this one. Square root of dv over g minus k over mv squared is just the same thing as square root of the partial fraction decomposition. We're gonna go write it. So we're gonna go plug this in here, our partial fraction decomposition, which is equivalent to, or which is equal to 1 over g minus k over mv squared. So this one here, we're gonna go plug it in our integral. So we can actually factor out the 1 over 2 squared of g, because we don't want that in the numerator. So we're gonna have 1 over squared of g minus squared of k over mv. And we can also have plus 1 over squared of g plus squared of k over mv. So don't forget about the dv. We now have this one. So I want to factor out the square root of k over m so that it's easier to integrate. Factor out this one, integral of 1 over 2 square root of g. Factor out the 1 over square root of k over m, right? So we now have, if we factor out 1 over square root of k over m, we'd be left with 1 over square root of g times square root of m over k. So you just take the reciprocal and multiply this in here. Minus v, right? Plus 1 over square root of g times square root of m over k plus v. So I want that to be like that, is equal to, we can combine these ones here, 1 over 2 square root of jk over m times 1 over square root of gm over k minus v plus 1 over square root of gm over k plus v. So by writing this integral like this one, we can easily go get the integral of this. So we want these terms out the integral. That's 1 over 2 square root of jk gk over m integral of 1 over square root of gm over k minus v plus 1 over square root of gm over k plus v dv. So now we recall that the formula for like the integral of 1 over a plus x dx is just equal to ln of a plus x, right? So we use this one here. And the integral of 1 over a minus x dx is just equal to ln of negative ln of a minus x. So you just use this to solve for our integral. So we use that one to solve for the integral. That's 1 over 2 square root of jk over m. The integral of this, so we just imagine this as a and we just imagine this as x. So which formula do we use? This one. So that's negative ln absolute value of a minus x. Our a is square root of gm over k minus, our x is v, so we use that one, plus, this is plus, the integral of this one, if we let this as a and we let this as x, so which formula are we going to use? This one. The integral of 1 over a plus x dx is equal to ln absolute value of a plus x. So that's ln, our a is square root of gm over k, our x is v. So we have this here as our integral, 1 over 2 square root of jk over m. ln, by logarithmic properties, we can actually simplify this. So this is just the difference of two logarithmic functions. So we can make this as like this. We'll go make this in our numerator and this one here in our denominator. Well, over square root of gm over k minus v. See? We did that because we want our answer to be in a pattern where we can actually simplify it even more. And we can express it into some inverse hyperbolic function. So let's just go have a review with like inverse hyperbolic function. But before that one, we're gonna multiply both the numerator and denominator by square root of k over mg over square root of k over mg. Because I want to create a pattern like this one. I'm gonna show you 1/2 ln of 1 plus x over 1 minus x is equal to the inverse hyperbolic tangent of x. So I want to create this pattern so that we can actually simplify these term here into an inverse hyperbolic tangent function. Okay, so I want this to have like a 1 here so that I'm multiplying the reciprocal of this term here. Okay, so that's 1 over 2 squared of jk over m times ln. So what happens now? This multiplied here is just 1 plus squared of k over mg v over 1 minus squared of k over mg times v. So that's it. So as you can notice, we have 1 over 2 here. That's why we have 1 over 2. Oh, no, 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 no. We have 1 over 2 here. We have 1 over 2 here. We have ln. We have 1, 1, 1, 1. And we have this. Let's say this is x and this is x. See? We successfully created a pattern like this one. But before we can express this term here, the ln of the absolute value of 1 plus squared of k over mgv over 1 minus squared of k over mgv into this simplified form here, the inverse hyperbolic tangent function. So but before we're going to do that, we're going to prove first that 1/2 of ln of 1 plus cv over 1 minus cv. Our c being this one, okay? Our c being squared of k over mg. For the meantime, we're gonna use c because it takes too much effort to write this like term here, squared of k over mg. So we're gonna go prove this, that this is equal to inverse hyperbolic tangent of CV. Okay? So we can do that by letting this whole expression here be equal to y. 1/2 ln 1 plus CV over 1 minus CV is equal to y. So we'll multiply both sides of the equation by 2, would be left with ln of 1 plus CV over 1 minus CV is equal to 2y. So that means we can actually say that e to the 2y, because we can raise both sides of the equation, we can make this e to the ln, absolute value of 1 plus cv over 1 minus cv is equal to e to the 2y. So our e to the 2y now, we can write it as 1 plus cv over 1 minus cv, right? So, because we can cancel these two out. And that's just a property of logarithm. So, we multiply both sides of the equation by 1 minus cv. So that we'll have e to the 2y times 1 minus cv is equal to 1 plus cv. So we have this one is equal to e to the 2y, distribute e to the 2y minus e to the 2y cv. Okay? So we group terms with the same variables. We subtract 1 to both sides of the equation. So that's minus 1. If we subtract 1 here, we also subtract 1 here. Would be left with cv is equal to e to the 2y minus 1 minus e to the 2y cv. But we also want this term here to be transferred there, so we're going to add both sides of the equation by e to the 2y cv. E to the 2y cv. This is c. So these things here are cancelled because that's just 0. So we can factor out the cv. So that's e to the 2y plus 1 is equal to e to the 2y minus 1. So divide both sides of the equation by e to the 2y plus 1 over e to the 2y plus 1. So we now have cv is equal to e to the 2y minus 1 over e to the 2y plus 1. So we multiply both sides of the equation by e to the negative y over e to the negative y. That's 2y minus y, that's e to the y minus 1 times e to the negative y. We have this. And e to the 2y times e to the negative y, that's 2y minus y, is we're left with e to the y plus e to the negative y. So as you can see, this one here can be expressed as the hyperbolic tangent of y, right? This is the hyperbolic tangent of y. And you remember what the value of y is? We let y here. Y is just this one, the inverse hyperbolic tangent of CV. So let's go plug that in here. The inverse y is just the inverse hyperbolic tangent of CV, right? This one here is this one, inverse hyperbolic tangent of CV, that's y. Like if we do the inverse, we also have the hyperbolic tangent of y is equal to CV. We just do the inverse of this one, we'll get this one. And as you can notice here, our hyperbolic tangent of y is this, and our CV is this. So we just proven that this formula here is true for any c. So now we can use this formula here to simplify this term here, okay? Because this is just similar to having our c here, okay? So we'll just make this the inverse hyperbolic tangent of CV, where c is square root of k over mg. Okay. This one here we can express as the inverse hyperbolic tangent of CV, or c is square root of k over mg v, okay? So now, this is the answer for our integral, right? This is the answer for the left-hand side of our equation, which we integrated before. This one here, you remember? This one was our original equation, and we found this. So we found this left-hand side of the equation as that one. So we'll go write this integral again. We'll go write this down for you to remember. So this is the integral of dv over g minus k over m v squared is equal to the integral. This was our original integral of dt. So our answer for here is actually the left-hand side of the equation. Our answer was this one, but we just simplified it to make it in this form, the inverse hyperbolic of tangent. So that's 1 over 2 square root of jk over m. So that's 1 over 2 square root of jk over m times this one here, ln absolute value of 1 plus square root of k over mgv over 1 minus square root of k over mgv. But we can write it as this one, the inverse hyperbolic tangent of square root of k over mgv. So we'll write that down instead. So the inverse of hyperbolic tangent of, what was that again? Square root of k over mg over v. K over mg times v, is equal to this one here, dt is just t plus c, right? From some constant c. Let's go solve for v. We can actually transfer this, multiply both sides of the equation by 2 square root of jk over m, right? So we'd be left with tangent, the inverse hyperbolic tangent of square root of k over mgv is equal to t plus c times 2 square root of jk over m. Oh no, let me correct myself. This one here is now like gone because we've already converted this part here. This, the 2 actually is like part of this one, the 1/2. So I'll just go rewrite that to like not make me confused. Let's go delete it. So that actually is 1/2, what was that again? 1/2 ln of 1 plus square root of k over mg. 1/2 ln of absolute value of 1 plus square root of k over mg v over 1 minus square root of k over mg v is equal to the inverse hyperbolic tangent of square root of k over mg v. Okay? So I was wrong. I still included the 2 here, so it should not have a 2 here. So we'll go delete these 2 because I was a little bit confused. This one here will go delete. And this, no, I mean only this. We'll go delete that. We'll go delete this. So now we have a very good equation. We now like go take the hyperbolic tangent of this right hand side expression here, that's t plus c times jk over m is equal to square root of k over mg times v. And next is we multiply both sides of the equation by square root of mg over k. That's square root of mg over k times hyperbolic tangent of t plus c times square root of jk over m is equal to v. So now that we have an equation for our velocity with respect to time, so we can say that this is velocity with respect to time, that's v of t. But we want to express these in terms of vt. You remember our terminal velocity is equal to square root of mj over k, right? As the forces balance, where the acceleration of the body that's free falling is equal to 0, your terminal velocity now will get square root of mg over k. So we'll express this one as vt. This one here, that's vt. And how about this one, square root of jk over m? We can actually express this as g over vt. We'll go derive. I'm going to show you that it's equal g over square root of mg over k. So you bring the square root of k to the numerator, square root of k over like times g over square root of mg. So that's g over square root of g is just square root of g, right? Square root of g times square root of k over square root of m. So that's why we have square root of gk over square root of m, or just square root of jk over m. So which is equal to this one here. So this, we're gonna go use this one. So because we want our answer to be expressed in terms of vt, that terminal velocity. So the final answer for our v of t is equal to this one here, square root of mg over k, that's vt, terminal velocity, times hyperbolic tangent of like t plus c times this one, square root of jk over m is just g over vt, the terminal velocity. Now we're gonna go use our initial condition, which is v of 0 is equal to 0. Since the body is in free fall at time t is equal to 0, its velocity is 0. So we're gonna go use that one. V of 0 is equal to 0 is equal to vt tangent, hyperbolic tangent of 0 plus c. 0 plus c, it's just c g over vt, right? But to make this expression a 0, this should be a 0. So we'll make cg over vt is equal to 0. So that's why rc is equal to 0. Okay? With given that initial condition. So The answer now for our v of t after a long derivation is the terminal velocity times the hyperbolic tangent of g over vt times t. So this is now our final answer. V of t is just equal to the terminal velocity times the hyperbolic tangent of g over terminal velocity times t. Thank you for watching my video.